All right, so next we have the ideal gas law. And the ideal gas law takes all of the other laws that we discovered. That was Charles's law and Gay-Lussac's law and Boyle's law and Avogadro's law. It puts them all together and says, hey, look, we know that at constant temperature for the same sample, my pressure times my volume is always constant. And we know that my volume is directly proportional to the number of moles. And we know that at a constant volume, my pressure is equal to the temperature, and a constant pressure, my volume is equal to the temperature. So we know that goes here. So really, all I need then is one last little piece, some constant that makes that equation work. And we're going to call that constant R. So R is the ideal gas constant, and I will give this to you on an exam. In fact, the constant changes depending on what unit we're using, but for the purposes of our class, we're going to be using liters and atmospheres. So R is 0.0821 liters times atmospheres divided by moles times Kelvin. This is just a constant, just whatever it takes to plug in here to make the rest of this work mathematically. So this is essentially when we were going back here and we're saying we have some constant K that would make it an equivalency. Here we're now finally defining what that K constant is if we put all of it together. That's what it comes down to. So this is awesome because in every previous example, we had to have initial conditions known so that we could predict something about the final conditions. Whereas here, I don't need to have initial and final conditions. If I just know several of these variables, if I know pressure, volume, and number of moles, then I can just solve for temperature. The value of R, Robin, does not change unless I'm changing the unit, and then that doesn't really change the volume, or the value, it just changes the units that it's being expressed in. Yeah. Okay. So for example, let's look at this. If I have something like 3.5 moles of oxygen at a volume of 27 liters, and a pressure hang on a second. Pressure of 1.6 atmospheres, then I can say what is the temperature. Okay. In other words, I give you a formula, and if I tell you what, let's see, we've got 5 different variables in here, and this isn't a variable, it's a constant. So we have 4 variables plus a constant. If I give you the values of 3 of those variables, you should be able to calculate the 4th. Okay. Again, I'm going to recommend solving this equation before you plug stuff in. So if we do this together, solving for t, because that's what we asked for, we're going to divide both sides by nr so that those will cancel. So we should get PV over nr is equal to t. Does everybody see that? Okay, and now we can just plug this in. Pressure P was 1.6 atmospheres. Volume V was, oh, here we go, 27 liters. N is the number of moles, N for number moles, 3.5 moles. And then R is this constant. I just plug this whole thing in. 0.0821 liters times atmospheres divided by moles times Kelvin. Now, I often have students that try to then plug in the 27 liters here. Don't do that. This isn't saying volume, it's saying this is units of liters that applies to that number. Okay, so don't do that. So this should equal T. And if you notice your units, atmospheres divided by atmospheres will cancel, liters divided by liters will cancel. Moles divided by moles will cancel. And then since I'm dividing by Kelvin, but I'm dividing by Kelvin, the Kelvin ends up on top. So I will get my units in Kelvin. Following your units will be helpful because if I gave you milliliters or something and you put milliliters here, you would instantly see that you're going to have to convert it to liters according to your use of the ideal gas constant in order to get the right answer. So that's just a heads up. I do always recommend that you carry your units around with the numbers as always. So when I solve for temperature here, what do I get? One 1.6 times 27 divided by 3.5 divided by 0.0821. Make sure that you put a 0.0. I think you might have dropped a 0. .6 times 27 divided by 3.5 divided by 0.0821. Okay, I'm getting at like 150. You guys, all three of you got a 1.01? Yeah. Yeah. Aha. Careful. I think I might know. Let's see. If you did 1.6 times 27 divided by 3.5 times 0.0821. Yep. Yeah, the problem is when you say 1.6 times 27 divided by 3.5 times 0.0821, then it multiplies this, it puts it basically on top. So you would need to, if you want to do that, you have to use parentheses to tell it the order of operations. 1.6 times 27, if you say divide by parentheses 3.5 times 0.0821, that should have gotten you the answer. Yes. Or if you don't want to use the parentheses, 1.6 times 27 divided by 3. And then I hit divide by 0.0821. So anything on the bottom, I'm dividing by everything that's on the bottom independently. That gets me 150. I just did the plus sign so that you could see the whole equation. This times that divided by that and divided by that. I could multiply these two if I put them in parentheses. Okay. But make sure, basically your calculator is gonna follow its own order of operations. And unless you tell it that you need to divide by both of these things multiplied together, it's gonna multiply the second one to the top. So careful, careful, careful on that. All right, good, I'm glad we saw that because that's a really common mistake. And my lecture notes converts that to 423 degrees Celsius, which is quite obviously wrong to me. This should be about equal to negative 123 degrees Celsius, if you wanted to convert that to Celsius. So whatever my lecture notes say about 150 Kelvin being Celsius, just ignore that. Because it should be 150, 150 minus 273.15. So yeah, about negative 123 degrees Celsius for your answer on that one. Okay, so again, ideal gas law, great. It's just algebra, and you can do that. All right. Additionally, we can use the ideal gas law to come up with something called the combined gas law. Let's see. Which compares initial conditions to final conditions. And that's where we can say if PV is equal to nRT, then PV divided by nRT is going to be equal to 1. That was going to be constant. So that's going to be PV over nRT. Initial conditions, final conditions. And you guys should recognize that if I'm talking about the same exact sample, my number of moles is the same, so that'll cancel. And R is a constant, so that'll cancel. So the combined gas law is going to tell me that the initial pressure times the initial volume over the initial temperature equals the final pressure times the final volume over the final temperature. And essentially using this method, you can take the ideal gas law, which I'll give you on a test for sure, and use it to deduce any of the individual gas laws that we just talked about in the last lecture, which I will not give you on the test. So if I'm giving you something with pressure and volume at a constant temperature, you say, oh, constant temperature. This is the relationship between pressure and volume. Or if I give you a relationship between pressure and temperature at a constant volume, you say, oh, constant volume. This then is the relationship between pressure and temperature. Do you guys kind of see how I use the ideal gas law to deduce what my individual gas laws are? You don't have to do it this way. If you want to memorize all 4 of the gas laws, go for it. But if you're not a memorizer, here's a logical way to get there. Yeah, whatever's constant gets canceled out because it's the same on both sides. So like you could divide both sides by the volume because it's the same volume and it would be gone. That makes sense. So there's a kind of a quick and dirty way to deduce what those individual gas laws are from the ideal, because I'll give you the ideal gas law. I will not give you individual gas laws. All right, so if we look at our 8.2 in-class activity sheet, this section 5 has to do with answering questions using the ideal gas law. And I'm putting this together with stuff that we covered in chapter 5. Okay, so here we go. 18 grams of oxygen, I give you a temperature, I give you a pressure, and I ask for volume. We're going to need to use PV equals nRT. And I hope you guys recognize that since R is 0.0821 liter atmospheres per mole Kelvin, we're going to need to use units of liters, units of atmospheres, units of moles, and units of Kelvin. I already have Kelvin, but I have millimeters of mercury. What do I need to convert that to before I can plug it into the equation? Perfect. I'm going to need to convert that to atmospheres. Atmospheres, Kelvin. Uh-oh, I have grams. What am I going to need to convert grams to before I can plug it into the equation? Moles. How do I do that? Can you guys do that? Use the molar mass. Okay, I'm going to trust that you guys could do this on the exam because I'm going to include that as part of what you need to do. So this first section is literally just make sure you've got everything in the right units and then plug it in, calculate volume. Done. Okay. This next one, I've got an equation. Oh, what's the first thing you're going to do when you see an equation? Balance. Is this balanced? No, it's not. I've got 2 aluminums. Okay, so first thing, balance that equation. Okay, then you can answer part A, which says I start with 5.7 grams of this, And I want to know how many moles of that could be produced. That's a question directly out of chapter 6. Use your roadmap. You're going from grams of one thing to moles of another. You guys can answer that. You did it on this last test. You did a pretty good job of it too. So I'll let you do that. Once I find moles of H2S, then I'm plugging it into this one. If I give you temperature and pressure and moles, can you tell me volume? How would I answer part B? You have temperature and pressure and moles of a gas. How do you calculate volume? Ideal gas law, exactly right. Your ideal gas law expresses the relationship between pressure and temperature and volume and number of moles. So again, you're just going to solve for volume, plug everything in. Okay. Would you guys like to do any of these particular problems before we move on to the next section? I'm gonna guess by your silence, you guys feel like you don't know what to ask. Okay, yeah. It really is just plug and chug. It really is just plug and chug. Robin, let's do this first one because then it's going to be kind of the same thing that you're going to do for part B here. So for this first one, millimeters of mercury to atmospheres, we can use that there's 760 millimeters of mercury in every 1 atmosphere. That's going to be our conversion here. For here, we've got 2 oxygens. They're each at 16. So we've got 18 grams oxygen, and we have 32 grams of oxygen in any 1 mole of oxygen. The hard part here is remembering that there's 2 oxygen atoms, and then remembering that the 32 goes with the grams. So that's going to give us moles of oxygen. Let's see here. So 18 divided by 32, we get 0.5625 moles of oxygen. And here's your temperature, 350 K, and then 550 divided by 760 gives us 0.724 atmospheres. Okay, and here's our temperature. So moles, temperature, pressure. We're calculating volume. So let me solve for volume before I do anything else. I'm going to put it down here. Solve for volume, I'm going to divide both sides by pressure. So I find that volume should be nRT over P. And now I just plug in the values. N is number of moles, which we calculated up here to be 0.5625. Moles of oxygen. There we go. R is my ideal gas constant, 0.0. Always remember the 0 there. 21 liters times atmospheres over moles times Kelvin. Okay, my temperature was given up here. It's 350 K. And then my pressure I calculated here is 0.724. And if we watch our units carefully, we see moles cancels with moles, kelvins cancel with kelvins, atmospheres cancels with atmospheres, and we're left with units of liters, which is great because that's what we were asking for was volume. So now we just plug it in, 0.5625 times 0.0821 times 350 divided by 0.724. And I should get a volume of 22.3 liters. Everybody follow what I did there? Just a little bit of practice will get you there. I think you guys are pretty familiar with algebra. 1 atmosphere is equal to 760 millimeters of mercury. And I give that to you on an exam too. That's the conversion between the two. Yes. Again, if you guys ever want to see what you get on an exam, you just go to our homepage. Let's see here. You should get this on exam unless I forget, in which case you just call me out and I'll grab it for you. But this exam support materials thing here, which has the conversions roadmap here, here's your equation. So there's a relationship between K and degrees Celsius. There's the ideal gas law. There's the value of R. There's a conversion between millimeters mercury and atmospheres. So you'll get those. You'll get this on the test. So that should be helpful. Some of these are less helpful. Like this is from chapter 10, so you're not even going to need that for this upcoming exam, but I just figured I'd give you one equation sheet and that would be good enough. So anyways, okay, so then part A here is a throwback to chapter 6. You can use that to calculate moles, which you could then plug into part B, which is the same as the ideal gas equation. You should be pros at that. Okay, we've only got 5 minutes left. I want to make sure that I cover this last little section on partial pressures before we go, because it tends to be a little bit of a confusing topic. But partial pressures looks at the relationship between the number of moles and the pressure, and discovers, no surprise, that the more moles you have, the higher the pressure is directly related. And since all gases behave exactly the same way, because their particles are so small that they don't even take up that much space, and they're so far apart that they don't attract or repulse one another, we find that this is true. In fact, the ideal gas law is true of mixtures of gases just as well as it is for individual gases. So, in other words, when I say that PV equals nRT, I don't have to be looking at, say, a sample of oxygen or a sample of methane. I could just be looking at air and say, how many moles of gases do I have in air, and plug that in. Even though air is a mixture of, we've got a certain number of moles of nitrogen atoms or molecules and a certain number of moles of oxygen molecules. It's about 79%, about 20% number of moles of water vapor, number of moles of carbon dioxide. I mean, air is a complex mixture of all sorts of things, but really, you just add all these up, and then the total number of moles is what you could plug in here, okay? And so this is directly related, since the number of moles is directly related to the pressure, then we can say for any mixture, the pressure that's being exerted by a particular gas is directly related to the number of moles of the gas in that sample. So for instance, if we say that air is 78% nitrogen, then we could say the pressure being exerted by the nitrogen in the air is 78% of the total pressure, the total air pressure that we're feeling. So if, for instance, the air pressure on our skin at any given time is 14 pounds per square inch, then 78% of that 14 pounds per square inch, or 11 pounds per square inch, comes from nitrogen molecules that are colliding with the surface of the skin. Does that kind of make sense? You guys following me conceptually, if not mathematically? Yes, the fraction is always equal. Or in other words, we're going to say, when we say the fraction, that's this percentage here, right? So the number of moles of any component A, so in this case it was nitrogen, divided by the total number of moles, in this case that was 78%, is going to equal the pressure that's exerted by that gas A divided by the total pressure. In other words, 78% of the total pressure. So this fraction, or the percentages, are always equal. Yes. And here's how you would express this mathematically. Conceptually, you can imagine you've got a container, and you've got inside that container, you've got some red gas particles. Here we go. And you've got some green gas particles that are running around. And you've got some, let's say, blue gas particles running around. I'm putting arrows just to indicate that they're moving. They're not just like floating around, but they're actively moving. And if you stop to count all these, you'll see that in this container, I have 5 blue particles for every 3 green particles for every 2 red particles. Everybody follow me there? I specifically chose that number because it then adds up to 10, right? 10 particles here. 2 out of every 10 are red, so 20% of my particles are my red gas, and therefore 20% of the collisions on the surface come from that red gas. So 20% of the pressure that's felt comes from collisions from the red particles. And 50% of my particles are the blue particles. Therefore, 50% of the collisions, or 50% of the pressure that's felt, comes from those blue particles. And then 3 out of 10, or 30% of my particles, are green particles. Therefore, 30% of the collisions that are felt, or 30% of the pressure that is exerted in the container, come from my green particles. Excellent. Okay, so there's the theory. This is the mathematical equation that kind of expresses exactly that. Fraction of my particles is the same as the fraction of the pressure. If you look at our 8.2 in class activity sheet, this very last question has to do exactly with that. So I encourage you guys to look at it and give it a shot. Try it out and see if you can't give a good try at it before you come to class. And we'll talk about the answer on Wednesday. And that's it for lecture 5, number 3.